In question 1a, we're to define the term stopping distance of a vehicle. Well, this is the distance travelled between seeing the hazard and actually stopping, or the thinking distance plus the braking distance. In B, part 1, we have a train travelling at 61 kilometers per hour. We're to show that this is around 17 kilometers per second. Well, it is 61 times 1,000 to get into meters per hour, divided by 60 to be meters per minute, divided by 60 again to be meters per second. And this comes out at 0.94 meters per second, which is around 17 meters per second as required. In part 1 of part 2, we're to find the kinetic energy of the train. Well, kinetic energy is mv squared over 2, which in this case is 1.9 times 10 to the 5 kilograms times 17 squared over 2, which is 2.75 times 10 to the 7 joules. In part 2, we're to find the average deceleration of the train. Well, for this we can use v squared is equal to u squared plus 2as. So a is equal to v squared minus u squared all over 2s. S. This is 0 squared minus 17 squared all over 2 times 310. We're told it stops in 310 meters. This comes out at 0.47 meters per second squared. In part 3, we're to find the average braking force. Well, F is equal to ma. The mass is 1.9 times 10 to the 5, and the acceleration we've just found as 0.47 gives a force of 8.9 times 10 to the 4 newtons. In part 3, we have a similar train travelling up an incline. The brakes are again applied with the same average force. We're to state and explain how the distance will differ in this case. Well, the braking distance would reduce. Two ways of thinking about it. Some of the kinetic energy is now converted into gravitational potential energy, so less work needs to be done by the brakes. Alternatively, there is now a component of the weight acting down the slope. This gives an increased force opposing the motion.